So, good morning, everyone. Nice to see you all here this early in the morning. First, I have a question for you. What's on the picture? Anyone an idea? See several good answers indeed. So it's all chips. Memory, CPU, sensors, storage, whatever basically. And we basically use it in our daily lives. I mean, I see people now playing with their phone or with their laptop using all kinds of chips. 2 years ago, I joined ASML. Who knows what ASML does? Few people. So basically, we create the machines that the big chip manufacturers like Intel, Samsung, and TSMC use to create our chips. And then I learned quite a bit on how chips are actually created. And I found it quite interesting because for my entire life, I used them without actually knowing it. And I thought, like, hey, maybe that's also interesting to share with other people like you. So we were basically going to see how a chip is physically created and how Java software is involved in the process. It won't be any marketing story because our machines cost about 300 million a piece, and I guess most of you will have a little challenge in that. So yeah, how many chips do you use? It's getting more and more. I mean, we have all these self-driving cars nowadays with a lot of chips in them. Microwaves nowadays have chips in them so that you, when you are at work, you can already start preheating your meal before you go home. It's getting more and more. And there are some estimates that we will go to 41 devices per person. I hope we don't have to carry all of them with us, because then we probably need bigger cars or something. And an enormous amount of data. So this chip consumption is only growing and growing. We saw the chip shortage like last year or the year before. There was a really big shortage. Now it's quite okay, but the expectation is that it will catch up again, the demand, especially now with AI chips and things like that. What's this? Duke and a wafer. So a wafer is the basis to create chips. And on this wafer, you see 564 Dukes. You can count them if you don't believe me. That's about the amount of chips you can do on one wafer. It depends a bit on what type of chip you make. If it's memory or CPU, then it can be less or more. But this is about the amount. Normally, they actually are printed also on the edge. So you have some waste on the edges. But I wasn't aware of that when I created this wafer. So you learn new stuff every day. So this is a transistor. It's basically the basis of all the computer chips. And it has a drain, a gate, and a source. This was still when transistors were big, you could actually see them. And it works a bit like a water tap. So water flows out, you can control it, and then some amount of water flows out. With electricity, and it's, of course, with transistors with electricity instead of water, but the principle is the same. Probably a lot of you have heard about Moore's law. There are some different explanations for it. One of the explanations is you double the number of transistors on a chip every 2 years. And that's basically going on since 1970, so for more than 50 years. Which is a bit weird, right? If you compare it to other things that are being created, like we create cars. Are cars getting twice as fast every 2 years? Are buildings being built twice as tall every 2 years? Of course not, we won't be able to do that. But for whatever reason, we still manage to keep up doing that for computer chips. So it's a really strange industry. So how small are we nowadays talking about when we talk about transistors and the size of them? So to put it into perspective, because for me when I started, they talked about nanometers. I had no clue, it's probably really small, right? 1 million nanometer is 1 millimeter. That's how small we're talking about. So I put some numbers here, like the sizes in nanometers. How big do you think that transistors are nowadays? 3 nanometers? Yeah, that's indeed about it nowadays. So we're going really quickly towards basically atom size. And yeah, compared to like a single strand of human DNA, it's almost unimaginable that we can create stuff like that so small. And why would we do that? Maybe you recognize this. This is Lord of the Rings. Maybe you read the book, saw the movie, or saw the new series by Amazon. We won't discuss it here. Probably it will end up not so nicely. This is a book of about 1,100 chapters. It's quite a thick book, even if they use really thin pages. If we would use 30 nanometers, which is still relatively big for us. And we print it. We can print it on a slice of A4 paper, 2,625 times. So that way, yeah, it's easier to transport. You can put a lot more in one truck to transport, a lot more content. Of course, it's a bit harder to read, but you have some challenges there. The same goes for computer chips. We want to have more memory on them. We want to have faster chips. And the smaller that transistors are made, the less energy they consume. So there are several reasons why it's good to have smaller and smaller transistors all the time. So when we create transistors, we start with the wafer, as I mentioned. And a wafer is created out of silica sand. Silica sand is something that's there in abundance. It's not some rare earth metal or something. However, if you ever see excavators digging up your local golf course, you should worry, because these golf courses also use silica sand. So normally it shouldn't be a problem. Then that silica sand, it's heated really hot, and they create a so-called ingot. It has a really weird shape, and apparently it's because they pull it out of the really hot melted sand. That's why it has this shape. And then this ingot is basically sliced, so they slice it vertically and create wafers out of it, so the wafer you saw with the Duke on it. And then here you have a collection of 25 wafers. In a factory, we don't transport them by hand or something, so we put them in containers like this. It's called a FOUP, front opening universal pot. 25 are in there, and they're automatically transported from one machine to the other machine. Then some more details about wafers. If you look at the machines, depending on the machine, the type of chip, one machine can produce about 330 wafers per hour, but that's a single layer, what we will see later. For a chip, we can have up to 200 layers. So layers are printed on top of each other, up to 200. As we saw, about 600 chips per wafer. The amount of transistors on one chip and per millimeter, it's quite insane, right? You cannot really imagine that we can print so much on such a small surface. So what we do looks a little bit like 3D printing. Maybe some of you do 3D printing at home. You can maybe start working for us as well. So we print layers on top of layers. But with a 3D printer, it's quite rough. When we look at printing two layers on top of each other, the accuracy we're talking about is comparable to driving a car across this line for 300 kilometers, then turning around, driving the same 300 kilometers back, only deviating a maximum of 2 millimeters across the entire road. That's the accuracy of lines on top of each other. So probably your 3D printer doesn't make that. First, the wafers, they are so-called coated. We put some chemicals on it called resist. It's in these machines. So the interesting thing is, well, we make some of the machines to print and to analyze if wafers are okay. There is like a huge chain of different machines, all sold by different companies. They can be mixed and matched together. And then with all those, you create wafers with chips. So here the chemicals are put on it. So you see it's all automatically, it's all in a clean environment with machines, no human that touches anything. And then it goes in this machine. Mostly at conferences, I say this is one of the most advanced machines on the planet. But yeah, yesterday I had a tour of Atlas, so probably I have to say it competes for second place now. So this is it's a huge machine. It requires 20 trucks to be shipped, 3 Boeing 747s, special shipping containers that make sure it's at the exact same temperature without too much shocks and everything. Containing several 100,000 parts only in this machine, delivered by I think like 800 global suppliers. So we don't build everything ourselves. There are a lot of companies involved in that chain. So inside this machine, and what's maybe also interesting, while we print smaller and smaller, the size of these machines with each generation becomes bigger. So this is already big, next generation even bigger. And why we will see later. So here you see one of the wafers. Normally there's not a person checking every time, of course, it's automated, but this shows the wafer laying there. And it's on a magnetically levitating wafer table, which means it's basically floating with the help of magnets. If we would clamp it, it would bend a bit. And things like that would already result in more faulty chips. So we do everything to produce as many chips as possible and as many functioning chips as possible. And that's why we do crazy stuff like this. So this wafer has that chemical coating on it, which we saw in the previous movie. And then in the latest generation of machines, we use EUV light to shine on it and in that way create patterns on the wafer. And how that works, we will see in this movie. So what did we see here? Basically, molten droplets of tin are being ejected at 70 meters per second. And then a laser, which is in the basement of the machine. So we saw the really big machine. The laser is actually in the basement because it's also just as big, basically, 450,000 parts. And that laser amplifies the laser pulse 10,000 times to 40 kilowatts. That laser beam travels for 30 meters and then exactly hits that droplet of tin. Makes it a little bit of a pancake. Then a second shot of the laser shoots at it again, hits it again, and then it results in plasma, which emits EUV light. So that's basically what you saw in the movie, which I think is crazy, right? That even that you hit it once, but this runs in production 24/7 worldwide, basically. Looks a bit like this. So this is not a UFO or something. You saw it being hit once. Now it's about to be hit for the second time, and then it emits the EUV light. And that resulting plasma has about the temperature of the surface of the sun, so we use gases and stuff to then again cool down the temperature, but need to remove the gases quickly, because then the next laser, of course, will shoot. So to do all that 50,000 times per second requires quite some calibration and figuring out. Then that light is created at one place, but it needs to be directed to some place inside the machine, and for that we use mirrors. These mirrors are super smooth mirrors with about 100 of layers of special chemicals to make them as smooth as possible and as reflective as possible. If you would stretch this one out to the size of Germany, one mirror, the biggest bump is 1 millimeter. You could use it to project an image on the moon with 20 millimeter accuracy. So it's really smooth mirrors. It's not the mirror you probably have in your bathroom. And then it looks like this. So we see the laser, or the light coming out here, produced by the laser. Then we have the mirrors, so it goes up and down a few times, up and down, and here is basically the wafer where we want the light to be. At the top we see something which doesn't look like a mirror. That's basically the so-called reticle. And a reticle is a bit like a stencil. Maybe you've used these in the past. When you were a kid, you could draw in them because some of the parts were cut out, and in those parts you can draw. A reticle is basically the same. It has the pattern that needs to be printed, cut out. The light shines through those parts, and the other parts the light cannot shine through. This is a real reticle. They're a bit more expensive, $250,000 a piece than your normal template that you use. So that's used to print every layer on top of that chip. So each layer can have a different reticle to print that specific layer. And then the printing basically happens You have both the wafer stage, which we saw before, it's at the bottom, it moves sideways, and we have the reticle stage at the top, and it also moves, and they move counterclockwise, basically, like this. One with 15G, the other with 5G, and somehow we managed to print at the right position, exactly. And of course, to do that, the wafer needs to be adjusted a lot of times to make sure it's exactly in sync. While the reticle, the pattern on the reticle is 4 times as big as the pattern that's eventually printed on the chip, so that you can make the reticle easier, basically, and cheaper. And that looks like this. So you see some parts the light goes through, and other parts the light doesn't go through. So this is the reticle handler with a reticle in it, used to produce patterns on a wafer. And then it looks like this. So on the right, you see the patterns being printed. On the left, you see that the wafer is analyzed. So it's sort of pre-calibrated, and then it goes to the right table to be printed. And they do that basically to save time. And now they can do the pre-calibration at the same time that another wafer is being printed. And while the wafer is being printed, they do extra calibration stuff. So it's basically parallelism, what we're doing here. And here you see the entire machine. At the top you see the reticles being, oh wait, this is easier. You see the reticles being changed, and here is the reticle. At the bottom we see wafers being changed, and they go in the machine there. So one wafer, I didn't explain that, it's about 30 centimeters in diameter, so it's not like really huge. Before you also had smaller wafers, I think some companies still use them, but 30 centimeter was seen as the most economically and practical size, because if you make them bigger, again, it tends to bend a little bit, which again isn't really helpful for your chips. So what happens then? We saw some nice pictures and videos, but basically this is how it goes on. First we have that wafer, then that photoresist, the chemicals put on top of it. Some light is shining through the reticle. Some parts of the photoresist receive some light on them, others don't. And then depending on what we want, we can either remove the parts where the light shone on or remove the other parts. And that's basically how we build layer for layer with transistors and connections between those layers. And it all goes in like a circle. So exposure in the middle, that's basically the part where we print. The step before, the coating, we saw that as well. It's putting the chemicals on it. So when you have 200 layers, you go through this circle 200 times. Could be with different machines. So we could use like newer machines to print really small details on one layer. And then in the next layer, where we don't need that amount of detail, we might actually use an old machine that could save cost. And maybe the old machine is even faster because it doesn't have to be as accurate. So that's still a combination of a lot of machines from a lot of different companies. You also see here metrology and inspection. We come back to that later, where we check how well the layers are being printed. And this can take a while. So it's not that a wafer is created in a day or something. It's a process that takes longer time. Every time we have to do the baking and things like that. So it's not you do 200 layers in one day and you're done. No, it is over a time period, depending on the customer and what they want. Then what we saw until this far is mostly about EUV. So with EUV, we use mirrors instead of the older machines with DUV that use lenses. And we need those mirrors because if you use lenses, EUV light is absorbed. So then you no longer have EUV light and we cannot use it. With EUV, we can print smaller details, basically smaller transistors, but it's also possible to print features that require 3 layers in DUV. We can print them in 1 layer with EUV. So there are a lot of advancements in new generations of machines. And the funny thing is that from the machines that we sold in the last 30 years, 95% is still running. Now, of course, they receive upgrades and maintenance and stuff, but I think it's quite impressive that these machines can run for such a long period of time, maybe creating less advanced layers or create less advanced chips. Like if you have some sensors in your microwave or something, they don't need to be printed on the newest generation of machines. And this then is how it looks like if you have a real wafer with real chips on it. So yeah, always looks quite nice. If you want a wafer at home, you can just buy them on eBay actually with these prints on them. No idea if it's completely legal or how they got them, but there are many there. Then if we look towards the future, which is already approaching quite quickly, because in the future we move to high NA, and the first machine was actually shipped in December, so last month, to Intel, but it's still in like the research and development phase. It's not that if we ship a machine, a new generation of machine, that the customer unwraps it and starts producing chips for us immediately. They need to adjust their processes, maybe even design new chips, new patterns, maybe new reticles, stuff like that. But this is like the next generation, and each generation mostly takes like a couple of years, like 8 or more years to create. So we expect in a couple of years that 2025 that they will start producing chips for us. So what is this NA? Basically, we try to focus the light so that we use the light as good as possible. On the left, you see the really old solution. You see that light is basically bouncing back and forth. It's not coming in the right position where we want to have it. Then we added water, and the light is better focused so we can print more fine details. This is not new, so we use the water already for a long time, also in our old machines, but this is the easiest way I can explain the NA stuff. So that's why I included it. For the new generation, what we will actually do is we will use new mirrors, and these mirrors are even smoother than the ones I explained before, so yeah, you probably read it quicker than I can explain it. But these mirrors, I explained that with each generation, the machines become bigger. And this mirror is an example of that. The old mirrors, they weigh about 123 kilograms each. The new ones weigh more than 1,000 kilograms each and are massive in size, 1 meter in diameter. So transporting these mirrors, you can imagine, it needs to be really careful, because if they break, have a dent, or even if there is a dust particle on them, they might be useless. And if you look at it, so on the left you see the old machine printing stuff, on the right you see the new machine printing stuff, so you see it's also a lot faster. And if we look at the reticle, so on the left you see the old reticle, 15 Gs. On the right you see the new reticle, 32 Gs. I thought it was one of those funny movies where at the end it would break out and shoot somewhere against the wall. But apparently this works 24/7 somehow. And next to these new generations, we also expect more and more measurements. Software is becoming increasingly important. It is already vital. Without software, you cannot produce any working chips. But the smaller the details get, the more we reach the hardware limits, the more important software actually becomes. And we actually get billions of measurements for each wafer that we process, which we can then use to make sure we recalibrate the machine. Because in the end, the goal for these machines, or for our customers, is to have as many wafers per hour with as many functioning chips as possible. Then they make most of the money. So how do we do that? We start with really clean rooms. So you see from NASA, the Americans, they are relatively dirty people. But probably they don't need it. For us, it's really crucial that we need really clean rooms. So in our company where we assemble the machines, it's really clean. Our customers, they have really clean rooms. And the biggest contamination is basically us humans. If we walk in there, the rooms, they measure also the particles floating around. You can see it go up as soon as a human enters. Humans aren't even allowed to wear perfume in these rooms, because perfume particles can already interfere with the production of these chips. It's so sensitive. But still stuff can go wrong. So my paint skills aren't really good, but this is a block. It's like if you print a layer and you look at it from the side, you see a block basically. If you print a second layer on top of it, it might deviate a bit. I mean, with the stuff we are doing with the laser, it can get warmer, maybe a mirror is slightly off. And slightly off in our case can mean it's like a fraction of a nanometer off in the right angle, things like that. So this is not really good, so we try to detect it and try to maybe print the next layer a bit to the other side to correct it. If we don't do that, you get stuff like this. So each line is printed a bit to the side, and in the end, all the lines fall over, and yeah, your chip is basically worthless. You can also have things like this, where lines are basically missing each other, or some sort of form of short circuit, where two lines are connected. So there are a lot of these different things that can happen. And it's not always a really big problem. So depending on the chip manufacturer and the design of the chip, they can actually build in like a redundancy. For example, if you have memory chips of 32 gigabytes, and we detect that there is a fault in one part, we might disable that part and sell it, or our customer sells it as a 16 gigabyte chip. Same for processors. I mean, in the past, you had Intel selling those Celeron processors. I think they publicly even stated that it was basically a normal Pentium, but then with less cores because they disabled some of the cores. So depending on the design, it doesn't have to be a disaster. Of course, we try to create as good chips as possible because then customers make even more money, but else, yeah, they try to circumvent it as well. And I think there are two main things that we try to detect. One is where you have issues on a particular wafer. Maybe there is a dust particle on the wafer. Then maybe one or a few chips might have issues. That's relatively okay. But if that same dust particle is on the reticle, and we detect it after 1 hour, then basically you have 200 wafers coming through with problems on it. So it's crucial that we detect issues quickly and try to fix them quickly. And as you see here, yeah, you can have a lot of different issues. Mostly when we look at these issues, we look at two different things. One is one layer is okay, and one is the overlay. And the overlay is basically what I explained before. So you put two lines on top of each other, and you check if they are nicely aligned on top of each other. We have some different machines for that to analyze it. So we have one machine to measure the overlay, and the other one to measure the critical dimension. And basically, that way we try to detect those issues. We cannot inspect every wafer in super amount of detail because then the testing would become a bottleneck for producing as many wafers per hour as we want. So it's crucial that we do like some tests and based on them try to figure out if other wafers might also have issues. And it looks a bit like this, one of the machines. So you see that FOUP with 25 wafers on the front. And this is the back. So we print in nanometer detail. You cannot really see with a microscope if lines are nicely aligned, right? So for some of these machines, we use diffraction with light and different colors to see if lines are nicely aligned. It sounds really weird, but apparently this is a nice way to detect if your lines are printed well. And that way we can basically see, okay, do we now need to adjust something in our machine, or is everything going okay? And a machine like this, it can be coupled next to the big machine, so the printing machine, so that is basically one big machine, but you can also have one of these machines separately so that you use it for multiple machines. It's up to the customer to do with it what they want. And then we get a lot of measurements, basically. Each machine produces 31 terabyte of data per week, and customers can have dozens of machines, basically. So it's a lot of information to process. And we use that information to basically recalibrate the 100,000 scanner correction parameters. So we can do a lot of tweaks to make sure next layer goes even better than the previous one. And this amount of data probably will only increase in the future. We're measuring more and using more and more to recalibrate. And some of the recalibration stuff is already happening on the machine, sort of in real time. And the more advanced algorithms, they are basically performed at a later stage, which we will see later. So this is an example of what we can calibrate. This is a mirror. For me, it's a really weird mirror because it's actually more than 4,000 mirrors which can be controlled individually to basically control the reticle illumination. So this is one of the parameters that we can tweak, but also angles of mirrors, temperatures, how many gas is being used, all those things we can tweak based on the information we get. And it looks a bit like this. So on the top you see all the different machines. So we looked already at lithography. That's basically the industry term for printing stuff, which we saw before, printing the lines. Metrology is basically the measuring. You see that we can do that at different stages. And all that data is fed to what we call the virtual computing platform. On that platform, we can analyze the data and do with it what we want. And this is not running in the cloud. And nowadays, our cloud is hip. Everything is happening in the cloud. But our customers are really afraid that their data will become public, because then their competition might use it to improve their machines and their setup. And on the other hand, we don't want to share our algorithms because they are really secret. Some are patented, but some are even more secret, so we don't even patent them. So everything is running on-premise at customer sites. And at first I thought, it's probably some small server somewhere. But each of these has a couple of hundred CPUs, a couple of 100 gigabytes of memory, and that's where we run our stuff on, our Java applications. So we, on top of that VCP platform, we created the IACT platform. And the reason was that before, each of our departments that analyzed the data, they had their own application with their own look and feel, own way to import data, etc. That was used at customer sites, but it was a bit confusing because everything looked different. They weren't really fast. So then it was decided to create one platform and then have all the features that were built as separate applications as plugins inside that platform. So it has to cover a high data volume, and it should be both generic but also really customizable. So for most of the software that we have, some things are common, like each wafer has an ID, each machine has an ID. That's the same for all of them. But some of the plugins that we have, they work on plain data. Some plugins, they work on images. So it's completely different. And we need to store all that stuff and be able to support all those use cases, because otherwise people don't use our platform. So it's a bit like a train platform. One platform can have small trains, big trains, fast trains, slow trains. You somehow need to support all of them. And we do that in the basis with Apache Spark. So with Apache Spark, basically, you can distribute work across multiple machines. So you have workers. Each worker has a machine, and you distribute the work across those workers and then later integrate all the results together. To do that, we have 3 types of plugins. Data plugins, basically to ingest the data inside the platform. We have UI plugins that enable the customization of the UI to have different kind of plots, different kinds of visualizations per plugin. And we have processing plugins, which are triggered from the UI. And basically, in the UI, you say, okay, I want to select this data, and I want to run this algorithm on top of that selected data. And that algorithm is contained in the processing plugin. So these 3 plugins are then developed by whatever department we have that wants to run something on our platform. In a bit more detail, it looks like this. So we have solutions with a front end, which in our case is React with a bit of Spring for the back end behind the front end. But we also have some jobs running sort of autonomous without a real user front end. We store a lot of data, both the real data, but also metadata, which we can then retrieve quicker. Because with these amounts of data, it's also crucial that you can show something quickly in the UI. That's always a challenge with huge amounts of data. And we use basically any Java ecosystem tool we encounter that we think is interesting. So we looked at everything what was interesting. If new things come out, we try them. For example, we tried running on GraalVM, so not the native image stuff, but replacing your normal Java runtime with a GraalVM runtime. Then you don't need to create native images. You still have the benefit of the later optimizations. And in a lot of cases, it's faster, but of course it depends a bit on what you're doing. You should measure it yourself. But that way, by just replacing the JVM, you can get free performance benefits. So every time new stuff is popping out, we are investigating if it's interesting enough, improves the speed, makes it easier for our plugin developers or whatever, basically. And while the platform is built mainly in Java, of course Spark is a bit of Scala, so we have a bit of Scala code as well. We support a lot of languages, and we do that in different ways. For example, via JNI or via Kafka messages to Docker containers, and inside that Docker containers, those Docker containers, plugin developers are free to use any language. So they can use the low-level languages which they are used to. We have a lot of physicists at our company, a lot of people who are used to writing low-level code. Also, a lot of algorithms are already there, and they don't want to rewrite them in Java, so it's easy for them if we make it easy to integrate those. So it works a bit like this. So they have that processing plugin, which is written in Java, and inside that they can call something in another language. They can do some Java processing before, some Java processing afterwards, whatever they want, basically. And then, I mean, machine learning is hip, so yeah, this is the mandatory machine learning slide for my presentation. But apart from all the fun stuff you can do with machine learning, this is actually, I think, a good example where machine learning really adds something. So what we see here is a scan we made of one of the wafers. With this scan, we can detect about 70% of the issues. If we would make a slower scan and slow down the scanning process 8 times, we can detect 100% of the issues. But slowing down 8 times means we can basically scan 8 times as less wafers as before. So that's also not really what we want. With machine learning, we actually managed to keep the same speed and still detect almost 93% of the issues. So a really large bulk without sacrificing scanning other wafers. So that's, I think, a good application that you can use for machine learning. And then to support all of this, we created an SDK. So we created things like Maven archetypes, documentation. We have regular meetings with all the plugin developers teams. Because if you create a platform in the beginning, it's fun, as long as nobody uses it. Afterwards, you have users, and then you need to make sure everything is backwards compatible. You don't screw up stuff. But also that your users start using new features of the platform. So having a good communication is also really essential, and we are getting better and better in it. By now, we have several customers where this stuff is running. So yeah, it's becoming more critical, more serious every day. Before it was basically a proof of concept where we worked on for about 3 years. And to give you an idea of the size, we're talking about number of people that are working on it. Nowadays we have about 150 people working on the platform. So that's only the platform, not the plugins. Plugin teams is even more. Or I don't know if it's more than 150, but it's on top of the 150. So it's quite a lot. Of course, we didn't start with 150. We grew gradually. But that's the amount of people we're using to build this platform. So if you're thinking to build this at home, that probably will be a little bit of a challenge. And then this is what comes out. At first, when I saw this, I was like, yeah, okay, nice. Some things. What we see here is basically, this is a processing plugin. So in this case, it ran something called TDBB, some kind of analysis. Somewhere also some data is selected. We can configure how stuff is being plotted. So this, now we use wafer plots, you can use graphs, so whatever you want, basically, you can even customize it yourself. Here you see some examples. So this is a graph, this is the plot. You can change it, for instance, to compare layers of wafers or to compare multiple wafers with each other to see if something changed. Basically, whatever you want, you can do with it. And there are 2 main things which you see in this analysis. One is here. It's called CE. That's the correctable errors. And with the correctable errors, you see here that all the arrows point in the same direction. They point like this. So basically, we printed that layer a little bit too far that way. A little bit too far is like, I don't know, half a nanometer or something. So next, what we could do to correct that is print the next layer maybe a little bit to that direction. So that's a correctable error. We know how to fix it. Non-correctable errors, on the other hand, you see a lot of arrows here pointing in different directions. The colors basically mean how much the deviation is, so how serious the issue is. But you see there, you cannot really see how to fix this. Maybe we can have another more advanced algorithm that can detect some more correctable errors out of this messy looking plot. And we even have really smart people who can manually sometimes even find stuff that can be fixed based on these plots. But for now, after this algorithm, we cannot correct them. So that's basically, yeah, what comes out of the data after it's being analyzed. So this is used in the factories by our customer support colleagues and could also be used by our customers to correct whatever they are doing. So yeah, to summarize, sometimes I still hear Java is not suitable for fast stuff and it's old and everything. I think we do pretty large data, pretty fast stuff, and still the decision was made to do it in Java. And I think that works really well, especially because you have the really large ecosystem of tooling around it to check for quality, to do integrations and stuff like that. But what's really important, if you start your own project, don't try to use the same tool set. We didn't start with that tool set. We had REST calls before, we still have some REST calls. Later, for the important parts, we switched to Kafka for asynchronous messaging and streaming. But we went gradually. And the nice thing is, if you encounter issues, you can also see if you can somehow help the community. We, for example, use some programming languages where we actually did some fixes to make threading work because it wasn't supported properly by the language. So we're also trying to sometimes contribute back. And in the end, I think, yeah, this way we can relatively easy build cool stuff depending on whatever you want to do. And that was like the really quick introduction. So if you have any questions, you can ask in a second, but first I want to start a short video. So it's a little bit of a promo video, but it shows how the wafers actually were transported through the factory. So it's all automated, going around, processing a lot of wafers each day. So that's to quickly show you how that works. Any questions? Because I think we have more enough time. Yes?
Yeah, when we talk about chips, we always mention Taiwan and US. You mentioned Intel. What is the European market? How many customers from Europe? You know, what is Europe doing?
There are some. You have some smaller chip manufacturers, like in the Netherlands. We have, for example, NXP, who also makes chips. But the bulk is coming from the big companies, all of you probably know. What you see now is that the European Union is sponsoring more of these companies to also build factories in Europe. So factories are being built in Germany. For example, near Dresden, there are a lot of factories being built at this point in time. In Dublin, Intel, I think, is building a new factory. So slowly there is more coming towards Europe, and I think the same goes for the US. They're also building new factories, and they subsidize it quite heavily. So you see that slowly some of it is coming back, but I mean, you can't underestimate it. Building a factory costs billions, even if you receive some subsidy. But that's still a relatively easy part. Then you need to get machines. I think we now have a waiting list of 2 years for new machines. Then you need people to operate them. You cannot get people from university and let them operate it. It's too complex. I mean, our machines are operated by our colleagues because companies like Intel and Samsung need help. I mean, they know a lot about it, but still. I think it was a colleague of mine who also made the remark, like with the global chip shortage, we can try to attract knowledgeable people, but then either we get them from our competition or from our suppliers. So it won't help the global chip shortage. You need to train people, and it takes time. And I think some of the new factories being built in Europe are actually postponed because they don't have the people yet. So yeah, knowledge is a really important factor, and it doesn't scale as easy as some people would want.
Yeah, there is another French-Italian company, STM Microelectronics. I don't know if you know that. They are building a factory close to my place in Milano.
Yeah.
They have the same problem about people shortage, yes.
Yeah, so there are a lot of small chip manufacturers in Europe, but I think if you look at like the global production location for chips, most is still in Asia. Slowly picking up, but I mean, you're talking about huge factories that are built in Taiwan. You cannot just build them in Europe with huge amount of machines. They don't have one of our machines. They have like rooms full of these machines. Yeah.
How many machines do you build per year?
So how many machines do we build per year? I don't know exactly for all of the machines. So we sell different kinds of machines. But I think for the EUV machines, I think it's a couple of dozen or something like that. So it's not like mass production. It's getting more every year. We're growing really fast, but demand is still higher than supply.
Do you see any
Yeah. Yeah, so the question is, how small can you go, basically? I think it's a wonder for everyone. Maybe really smart colleagues of mine who are more in physics know more about it, but I think we're already talking about these limits for years, and we still manage to go smaller. So for now, we still go smaller, but yeah, we're reaching atom size levels, so maybe there is an end towards it, but no idea. I think I saw a hand somewhere there before. Yeah. So the question is, how do you define the plugin contract? So we created APIs and stuff inside the platform, which the plugins can then use to build their plugins. And they can communicate sometimes also with us via Kafka. So we specified some messages that they can send back and forward. And we're also looking into using Spark Connect, so plugins can directly from a Docker container plug into Spark. So there are various ways where we can communicate. JNI is another one. So yeah, it depends a little bit. We try to support as many stuff as possible. Yep.
Which Java version do you use?
So the question is, which Java version do you use? You hope to hear that we're using still 8 or? No, it's various versions. So there are some parts that are using relatively new ones. I think some are currently being upgraded to 21 actually. Some are lagging a bit behind because our platform has a bit of an older version of Spark, and the Java version is coupled to Spark. So in some parts we cannot upgrade as fast as we want. We are looking into that and we're now trying to manage Spark ourselves, so then we can upgrade everything ourselves, and then we probably move to 21. Because basically selling it to the business is always difficult with these kind of things, but we are looking at improving milliseconds of time, and with Java each version can even give you some free performance benefits. So yeah, the investment is relatively small if you can just update some Docker containers, which we want to go towards, and get those benefits. Yeah.
What's the oldest piece of software that is running on these 30 years old machines, and how are you dealing with that?
So the question is, what's the oldest piece of software running on these machines? So my department doesn't run anything on the machines. It's different departments. So I have no clue what the oldest stuff is. But I think even some of that is built in hardware. How you call it, the FCPGA stuff. So it could be that there is some stuff that's already 30 years old. I'm not sure about that. It's a lot of C on those machines and low-level code. Yeah. And really strict processes, because there if you screw up and it costs a day of downtime for the machine, it's a challenge because 1 day of revenue is missed, but they also need to ramp down the machine and ramp it up. So it could actually cost like a week or something of production. So they really want to keep the machines up and running. I think we're already out of time. So I would say thank you all and enjoy the rest of the conference.